So, we talked about issues, foundational issues within mathematics that arose from Fourier and Cauchy having these arguments. We talked about foundational issues with measure theory and trying to extend measure to all sets. I put a link to Solovay, axiom of determinant choice, that there's a model in which you can still make every set measurable. These issues, the foundations of real analysis, are we can spend the entire semester on, as I mentioned. I do want to touch just a few baby steps in what has been done, what the process has been, just so that you know what's out there. And if you really want to go into that, we have a great department here of logicians. But I do want to then immediately pass to Lebesgue measure and Lebesgue integration and so on. So just as a first step, here's what people eventually came up with as what the natural numbers are. The natural number 0 is the empty set, which has cardinality 0. The natural number 1 is the set whose only element is the empty set. The natural number 2, is it the set that contains the set 1?
You could do it that way.
You could do it that way, but then it doesn't have the right cardinality. So it's the set that contains the empty set and the set that contains the set containing the empty set. So it has two elements, this set and that set. And the natural number 3 is the set that contains the empty set and the set containing the empty set and the set which contains the empty set and the set containing the empty set. And it has 1, 2, 3 elements. And so on. Okay? So this is what people started. Once everything breaks, you have to go down to baby steps. So again, we're not going to do this. I'm just planting seeds in your head in case you end up going in that direction. So let's pretend we know what the natural numbers are. I'm not going to give the axiomatic treatment of Zermelo-Fraenkel's set theory. If that's the natural numbers, then the integers are thens and then minus, right?
And
so
0. Oh, we already have 0.
0 is a natural number. We're is it the French or the Americans? I forget which one. There's a French school and a German school where 0 is or isn't a natural number. For me, 0 is a natural number. So it's the naturals union minus the naturals. So that's completion under the additive law. Completion as a group, extension as a group. Let's extend it as a field. So Q is the set of all formal ratios P over Q for integers PQ. Q needs to be not 0. If I want to represent this uniquely, let's make Q positive. So I don't have an issue of which one is the positive one, which one can be negative. And of course I want to have them in lowest form, the GCD form. Okay? So that is what the rational numbers are. They're ratios of integers where Q is positive natural number. We know what the integers are. We know what the natural numbers are. Now comes the hard part. What are the real numbers? So there's a variety of ways of doing this, and they're all sort of equivalent, although you can get into hyperreals and all kinds of other surreals, all kinds of other issues. The definition that I prefer, and I'll explain why, is the following. So I sort of mumbled it quickly last time. It's the equivalence class of Cauchy sequences in the rationals. So let's unpack that. So what is a Cauchy sequence? So if I have a bunch of numbers, x, n. So in this case, we're talking about the rationals, but this is a completely general notion. That's the beauty of Cauchy sequences. You see, if you want to say, I have numbers converging to root 2, well, who the hell is root 2? You can speak of numbers converging towards somewhere without knowing where that somewhere is. So that's Cauchy's great insight. So we have some sequence. This sequence is Cauchy, is a Cauchy sequence. So Cauchy is now an adjective. This sequence is Cauchy if
For all
yes, yeah.
N,
For
capital N,
Mn.
there exists little.
For all.
yes. For
Maybe an epsilon as well.
yes. Let's start with the epsilon. For all epsilon, this is engineering. How close? If I want to get within epsilon, Of what? That's the issue. Within epsilon of what? Within epsilon of root 2, but we don't have a root 2.
Of each other.
Of each other. That's the beauty of Cauchy sequences. You don't have to say of what. Of each other. So for all epsilon, there exists some n, so that for all m and n greater than capital N, and I don't know why I always make little n the bigger one, if you look at the difference between xn and xm, that's always within epsilon. Yes?
So now epsilon has to be rational because we haven't constructed reals yet.
That is true. And there are arbitrarily small rationals, thankfully. Yes. That's right. That's right. We haven't constructed the reals yet, so we'll restrict epsilon to rational. Okay, so that's what a Cauchy sequence is. I don't know where I'm heading to, but for all future time, you could say, I mean, in a sense, you can say I'm headed towards x capital N. I mean, let's think about this. Let's really think about this. Here's a picture of n in this direction, and then here are the points. So here's x1, here's x2, here's x3, here's x4, and so on. Okay? What this says is after capital N, if I take, let's just say, here's x capital N. Yes?
The points then get closer to each other, but may be positive or negative.
That's right. So if I use capital, so I can take little m to be capital N, never mind that it's a less than or less than equals, I don't care about that. So that means that everybody in the future is within epsilon of him. But then if I make epsilon smaller, well, there'll be some other capital N, and everybody will be within epsilon of him. And so on. So that's how we're zeroing in on root 2, without ever talking about root 2. Okay? So that's what a Cauchy sequence is. So you can say the real numbers, so here's our definition of the real numbers, it's just the set of all Cauchy sequences of rationals. Ah, thank you. Okay? So the set of real numbers is all Cauchy sequences of rationals. There's a problem with this. What's the problem?
Oh, no, I mean,
Oh.
that was one of those.
Okay.
Is this equivalent to like the Dedekind cut?
This is so Dedekind's idea is very similar. It says take all of the rationals that are bigger than root 2 and all the rationals that are less than root 2. That separation is a cut that creates a real number that we'll call root 2. So it's a similar idea. It's somehow less, you have to say numbers that are bigger than root 2. And when you go to general abstract metric spaces, you don't have a bigger than necessarily, right? Even in R2. What do I mean by bigger than where? What are you talking about? So the beauty of Cauchy sequences is you don't need anything but the things you started with. So you complete a metric space by taking all of its Cauchy sequences and adding them on.
So what if the two sequences, xn and yn?
Beautiful. So this is way too big because there are lots of different rationals that will converge to root 2. Okay? So we want to take out, we don't need to choose a representative, we just want to take out all equivalence classes. So two Cauchy sequences, so a Cauchy sequence xn is equivalent to a Cauchy sequence yn if and only if the difference xn minus yn goes to 0 as n goes to infinity. Which again, we understand what that is in terms of for every epsilon, there exists a capital N, so that this difference is always at most epsilon. Okay, so two Cauchy sequences are equivalent by definition if just take the nth term, take the difference, does that converge to 0? So that is a nice model. Now, if you haven't thought about these things, this is a massive, giant space of all possible Cauchy sequences and the rationals. We're going to mod it out by this kind of crazy equivalence relation that you have to check infinitely many terms to verify. But this makes the rational numbers the real numbers a very nice set from which to do things.
Is this standard metric? The metric?
Excellent. So this is all with respect to the standard metric, the standard norm, the standard absolute value. So let's talk. The reason I like this so much is because it immediately lets you define the P-adic numbers in the same way. So even though we're not doing any P-adic analysis, just for your information, I want to explain why this idea is so powerful and the general things that it can do. Okay, so let's recall what an absolute value is. how far back do I want to go in the foundations? I do want to show you this because this is kind of cool if you've never thought about it or played with it before. So what is an absolute value? An absolute value, some people make a distinction between absolute values and norms or places. Places are equivalence classes of absolute values. How do I want to say this? Do I have a good way of saying it here? Fine, let's just talk about Q, an absolute value on Q. What are the possible absolute values? So it's a function. Let's call it that. It's a function that takes rational numbers and returns, I want to say real numbers, but I don't want to say real numbers without defining real numbers. No. Let's return rational numbers. That's fine. With the properties such that is a function such that. What are some of the properties? First of all, it should be non-negative. Second of all, it should be positive definite. So if it's 0, the only element that's allowed to have norm 0 is the 0 element. We want it to be multiplicative. And there's one other extremely important thing, triangle inequality. Okay? There is a beautiful theorem of Ostrovsky. This is in 1916, just so you know, which classifies all absolute values. So classification of absolute values is there are 3 types of absolute values under rational numbers, up to equivalence. Let me not even say what equivalence is. If you take, I'm about to say it. If you take one of these and you raise it to some power, then depending on if it's an Archimedean absolute value or a non-Archimedean, which we're about to discuss, depending on the right power, sometimes you need the power to be less than 1. 2 absolute values are equivalent if whenever something has norm less than 1 in one absolute value, then it also has norm less than 1 in the other absolute value. Should I write that down? Absolute value 1 is equivalent to absolute value 2 if for all x, absolute value 1 is less than 1, let's call it strictly less than 1, if and only if absolute value 2 is strictly less than 1. And then it's not hard to show that that happens only when 1 is a power of the other. Okay? And the classification is, so what are the absolute values? Well, 1 is the one that we all know and love, the absolute value, which we'll call absolute value infinity. It's the place at infinity. Another one is also very trivial. I gave it away.
Everything's 1 except for...
Yes, the absolute value of x is either 1 or 0. It's 0 if it's 1, and it's 1 otherwise.
Discrete topology one?
Yeah, the trivial one. And the other one is the one that maybe isn't immediately obvious that it should be something that you should do, but actually already Hensel's lemma from 20 years before Ostrowsky tells you that this is the right thing to think about. Does anybody know what I'm about to write down? Is this news to... Okay, so there are a couple of people for whom this is not news, but what's the other... So let me not pick on Justin. What's your name?
Ishan.
Ishan? Yeah. So what's the other absolute value?
It's... You look at the prime decomposition of the top and bottom,
Uh-huh.
the lowest form, right? Pick a prime that you like, and then choose 1 over some number between 0 and 1 to the power of that prime.
Great. And up to equivalence, we can choose that number to be 1 over p. Great. So let me say that back to you. So any rational number can be written as a over b times p to the n, where n is an integer, positive or negative, with a and b co-prime to p. So you fix a prime p. There's 1 for every single prime, 2, 3, 5, you know who the primes are. And you declare this norm to be p to the minus n.
Then n is some integer.
Yes, there's a unique representation of every rational number. Once you've fixed your p, let's say 5. Okay, let's just see this in action.
Need to be prime, right?
P does need to be prime.
It does need to be prime.
Yes, yes. So the theorem is that the only absolute values are the p-adic norms, the trivial, and the Archimedean. And if you really want to, it's like a 10-minute argument. It's not that hard. And it doesn't use anything you don't know. Okay, you can kind of see that. So just for practice, bless you. How about 1 plus 3/17 in the 5-adic norm? Take a second, work it out. What's the norm of this? Give me a hand when you know the answer. Okay, you know the answer. You know the answer. Okay. Okay. Amazing you guys don't have to write this down. I actually have to write this down. Okay, so 1 plus 3/17, I just wrote it like that so I could hide the 5. 20/17. 20/17 is 5 times 4/17. The 4/17 contribute nothing. 5 is 5 to the 1. So the norm of this, the 5-adic norm of this is a fifth. Okay, everybody see that? Okay, exercise, if you really want to understand this exercise, this is an absolute value. The only thing that actually has to be proved is the triangle inequality. And when you think about it for a second, there's an actually much better triangle inequality for this. Justin, something's wrong?
Oh, so the coefficient of the coefficient, there's like an m.
That's an n, yes.
Okay.
Let me try to make that a little bit bigger. So whatever power you had, you put that power in the denominator. If I had a giant power of 5 in the denominator, I would have the valuation of that would be a huge power of 5. Yes?
So that is an if and only if for the absolute value x of 1.
Yes, that's an if and only if. This is really bad. I will try to write bigger because it's not giving you a very clear picture. Can I do this? Is that somehow better? Is it that it's taking an image? This is a nice geometry problem. There's a stereographic projection that it's undoing to throw here, and so there's distortion at the edges. That's what we're.
Wait, so are each of the p-adic norms equivalent to each other?
No, each of them is inequivalent. There's one for each p.
Got it.
You want me to prove this for you next time? I have other stuff I really need to do today. But if you want, we can. It's not hard. What's that?
What is the other step?
What is the other stuff? Measure theory. What we're here to do. This is the stuff that we're not here to do. This is not the quiz. This is just for fun. This is just because you're in grad school. You should know this stuff. Yes.
So is there some I don't know if I'm not seeing this, but is there some proof that says that these are the only ones?
That's the theorem. That's Ostrowsky's theorem. These are the only ones up to equivalence.
How would you go about arguing? You're
Ah.
saying that that's an easy proof?
Well,
Like 10 minutes?
it's 10 minutes. I mean, it was a major theorem. It still is.
Right.
It's
It
not.
just seems very, very,
Well, you start analyzing what the options are. You start seeing, are there integers who have a norm bigger than 1? If not, then are there integers that have a norm less than 1?
Right.
And you start playing these games on prime factorizations, and it's really not bad. I would rather, since I'm already giving you all kinds of stuff that I'm not supposed to be doing with you, I do want to get to some of the stuff I am supposed to be doing with you. This definitely isn't it. But if you like it, I don't care. They can go to hell. We'll talk about it. I don't know who they are. They is me, since I'm also going to be writing your real qual. Right. And the p-adic numbers are not on the syllabus. But I just say, okay, you really want to understand the p-adic numbers? First of all, yeah, I shouldn't be doing this.
Wait, so when you say p-adic numbers, do you just mean the rationals under the p-adic norm?
Ah,
Or do you
beautiful.
mean the completion of the rationals?
Yes, exactly.
Okay.
This is why that definition of the real numbers is so powerful, because we just change, mutatis mutandi, we just change all the words. So what are the P-adic numbers? The P-adic numbers are equivalence classes of Cauchy sequences. So these are Cauchy sequences. When we said Cauchy sequences, we didn't specify the norm. Which norm?
Whichever you want.
Whichever you want. Okay, so Cauchy sequences under the P-adic norm up to equivalence. And these are fantastic, very powerful numbers that you should really try to understand. There is a square root of 2 inside these. And just like you can write 1.414, you can write out a decimal expansion of Cauchy sequences. You can write a decimal expansion of root 2 in the real numbers. There is a root 2, and if you really want to understand this, it's an excellent exercise to write down its 5-adic expansion, which we can talk about how to do. I'm, again, getting way off topic. So let me, in the interest, now move on, but enough of you are kind of liking this stuff that maybe, and I like this stuff, so maybe syllabus can go to hell and we can talk about it. All right. Back to R. In fact, okay, what I should really be doing is abstract metric spaces. Maybe you've all seen real analysis over R. I don't know what the expected background is. I'm going to go a little bit slow, maybe, just to make sure everybody's on board. There was even this boot camp, right? So I don't know how much did they talk about any of this stuff?
Nope. It was
Good.
like proving Stirling's formula too.
Okay, good. We got stuff to do then. There are some funny things that happen over R that do not happen in general metric spaces, but already when you go to R squared, when you go to the plane, a lot of the funny things that happen over the reals disappear, and it looks a lot more like general metric spaces. We will get to general metric spaces. I first want to just make sure that we have all our foundations where we're comfortable. So the real numbers, we know what that means. By the way, decimal expansions are a great example of a Cauchy sequence. 1.4, 1 and 4 tenths, 1.41, 1 and 41 hundredths, 1.414, 1 and 414 thousandths. Those are all rational numbers that are converging to root 2. Okay? All right, so just some very basic things, right? And the norm, of course, if we're in RD, I will use so x is equal to x1 through xd, d tuple of real numbers. The norm is the Euclidean norm. You sum the squares, use the Pythagorean theorem. Okay. Back to that world. So if I have a set, let's just get some notation down. By EC, I mean the complement. So this is all the x in RD, which are not in E. We have to do some of this stupid stuff just to set the stage for everything. So this is the complement. If I have a set E, so this is E subset of RD, then by EC, I mean the complement. By E set minus F, which some people write E minus F, but there's good reason for this to have another meaning, so I will try not to use this. By E minus F, I of course mean all of the set of all x in E, which are not in F. So this is set complement. If I have two sets E and F, what is the distance between them? Other than Justin? Yeah. So the infimum of, now, if I want to make this applicable to abstract metric spaces, all I have to put is dxy, by which of course I mean the absolute value of x minus y, where x is in E and y is in F. Exactly. So that's the distance between two sets. Great. Open. So an open metric ball of radius r about x is the set of all y in your abstract metric space. I will keep writing r and rd to keep it simple, but I'll say what the words would be if we were doing abstract metric spaces, where the distance between x and y is at most r. So that's our open ball. Okay, a set is open. Subset. Well, so the norm gives a notion of open balls, which gives a notion of topology. So E is open. This is the most fundamental definition in point set topology. What does it mean to be open?
For all x and e, there exists a ball.
Exactly.
Contained in it.
That's
Perfect. For all x in every point has a ball around it that still sits inside E. For all x in E, there exists an R such that the entire ball of radius R about x is contained in E. Okay. That is open. What does it mean to be closed? Exactly. Very good. I'm glad you gave that definition and not the it contains all of its limit points. That is a theorem. Maybe we should prove that theorem. E is closed if E complement is open. Okay. Should we prove that theorem?
We could do P-adic stuff instead.
We could do P-adic stuff instead. I think we should. All right, let's prove it. For how many will this be a waste of time? Half. Okay. I don't mind wasting half of your time because the half of you that are going to tell me the proof. So E. I have to tell you what a limit point is. Definition. This is what happens when I go off script. I have a script. Everything's written out nice, and then you guys push me into juicy stuff that we got to talk about right now. What does it mean to be a limit point? X is a limit point or accumulation point. Limit point. Some people say accumulation point of E.
Every open set that contains x intersects E.
Perfect. If every open set,
Not
which we
trivial.
can just say for every ball of radius R about X, intersects E non-trivially.
Yeah, it also can't be at x
Yeah.
itself. I think it has to be for accumulation point specifically.
Right, an accumulation point is a limit point which is not in E, if you like. But some people just use accumulation point to mean limit point. Some of the notation is standard among certain classes of textbooks and not others. Right, so we know what limit points are, so now let's prove this theorem. E is closed if and only if every limit point of E is in E. Okay? So let's prove this theorem. Proof. All right, those that were going to be bored, Justin,
Use the complement.
use the complement. Okay, so which direction you want to prove first?
E closed.
Closed implies, okay, so let's prove this way. So assume E is closed. E is closed, i.e. E complement is open, and let X be a limit point of E, and assume X is not, all of these proofs are going to be by contradiction. Assume X is not in E. So I always draw a picture. I don't know why. It's the same picture every time. Here's E, here's the limit point.
So draw your ball around X.
Draw your ball around X. Every picture looks like this. I'm just going to keep drawing it.
X
Justin?
not in E means X is in EC.
Exactly, which implies X is in EC, which is open, which implies there exists some epsilon, so that the ball of radius epsilon around X is in EC, which implies
It doesn't intersect.
which the ball of radius epsilon around X intersected with E is empty,
Yeah, contradiction.
and that is not what a limit point is.
We didn't actually need a contradiction. We could have like erased the first few words there.
Right. So let's do it like this. Assume X is not a element of E. This is actually a very good thing to do because you start arguing by contradiction because that's kind of the natural way to argue. And then when you're done, you say, oh wait, this is a better way to do this,
Yeah.
which is just to remove the contradiction and remove the original assumption.
So
So
using the contrapositive.
yeah. Assume X is not an E, then X is in the complement. If it's in the complement, then there's a ball around it because the complement's open. If there's a ball around it that doesn't intersect E, then it's not a limit point. Done. Okay? Other direction?
So we want to show what you're closed if you contain every limit point?
Let's say you contain every limit point.
Okay.
Well, so for, so if it's, so say it contains every limit point, then you use something that, use the fact that the, every point in an open set is an interior point, right?
Yeah, so you like take a, so you want to show the complement's open, right?
Yep.
So take a point in the complement.
Let X be in the complement.
Can you move the paper up a little bit?
Yes, sorry.
So if it's in the complement, that means that it can't be a limit point of E, because E contains all of its limit points.
Okay. Implies X is not in the set of limit points, which I didn't give a definition to, so let's just say X is not a limit point.
Which means that you can draw a ball around
E
X that contains no points.
Implies there exists epsilon, so that the ball of radius epsilon around X intersect E is empty,
Yes. Which means that that ball lies entirely
which means
in
the ball
complement.
lies entirely in the complement, which means the complement is open. Okay, good. We're getting good practice because these are good warm-ups. Okay. What else did I want to say? Right, let's play little games with open sets. Lemma. If I in some arbitrary indexing set, not necessarily countable or finite, are open, then the union of OI is also open. Am I boring everyone, or are we getting something out of at least a summer has gone by and it would be good to remember how all these things go? So an arbitrary union of open sets is open. Proof?
Take a ball in at least one of them.
Right, if X is in the union, then X is in somebody, which means a ball of radius epsilon is completely contained in that somebody, which means that ball is contained in the union. Okay? And the same thing with intersections. Arbitrary intersections of open sets are open.
No.
Good. Okay, good. Just checking. Good. That's what I want. I want to make sure that you guys have that visceral reaction. Yeah, of course. Minus 1 and 1 plus 1 over n, the intersection of these over even a countable set is, of course, closed 0, 1. Okay? But finite, so let's write that lemma. The intersection of a finite number of opens is open. Proof? Okay, other than Justin and, tell me your name again?
Robert.
Robert. Other than Justin and Robert, tell me your name?
Charlie.
Charlie. Charlie, Justin, Robert. Justin, Charlie, Robert. Go.
So you get a ball for each of the OI.
Exactly. So X is in the intersection, implies X is in OI for all I, implies there exists an epsilon I, such that the ball of radius epsilon about X is in OI, which implies that the ball of, the minimum of the epsilon i's is contained in I for all I, so it's contained in the intersection. Good. All right, some games with point set topology. We're going to get to some non-trivial games, probably all familiar. All right, a few more definitions. E is, in a metric space, is bounded. So, okay, how would you do this in a metric space? What does it mean for a set? If and only if, that's the definition, there exists some R such that the ball of radius R about some point could be 0, but if I don't have a 0 in an abstract metric space, if there exists an R and there exists an X in my metric space, so that the metric ball of radius R about that point contains E.
So the empty metric space is unbounded, so you can't find a point to put the ball around.
It's also, it's, let's not deal with the empty metric space. You're right that yeah. Every theorem will say, assume the metric space is not the empty metric space, then let's prove something, okay? By my definition of a metric space, it's not empty. Let's do that. Okay, what else? All right, here comes a extremely important definition, which I was actually shocked. It's too late to argue with Eli Stein about it. Unfortunately, he passed away in December of last year. But he just says the real numbers satisfy the Heine-Borel property. No, that's a major theorem. We got to prove it. Come on, it's real analysis. So, definition, E is compact. Compact. Well, this is the definition. What does it mean to be compact?
Every open cover is a compact.
Every, oh gosh. Where's the garbage can? I'll throw it out later. Experiencing technical difficulties. Let's try that. If and only if and only if every arbitrary open cover has a finite subcover. So let's parse that, i.e., if you have some indexing set which is arbitrary, and you have a bunch of open sets, and they cover E, okay, so the picture is, here's E, I have a bunch of open sets, arbitrary, I'm drawing uncountably many open balls right now, believe it or not, then there exists a subcover, a sub-indexing set, which is finite, such that if you restrict yourself just to the open balls in that indexing set, it also covers E. So I only drew finitely many balls, actually, believe it or not. It looked like uncountably many.
Does this need to have an axiom of choice to define compactness?
No, I am not choosing, I'm not saying that there exists a point in each of these open sets. I'm not saying that I can choose a point in each of these open sets. Yes, Justin?
The Econoff theorem is something that relates to axiom choice, but this
Yeah, yeah. We're going to get to Tychonov later, but this, no. I'm going to say no, authoritatively. Yeah, I'm pretty sure no. Yeah, I don't know. We're not choosing. The axiom of choice is if I need to find a point in each of these OI. I'm not trying to find a point, I'm trying to find a subset of a set. Not a subset of
Each set.
Yeah.
each set.
And all of the open sets could technically be the empty set or something. Even.
Yep. Throw in, yeah. No, the empty set is open. So
Yeah. They couldn't all be unless your set was empty though.
Yeah.
all but you could have you can throw in,
Yeah.
take a finite cover, throw in infinitely many covers by the empty set.
Yeah.
Take them out. Okay. Good. Are we up to Heine-Borel? I have to give you some more definitions. Heine-Borel. I wanted to explain a little bit of the history. So, this is a wonderful thing. So, Dirichlet, remember we had this discussion about Cauchy and whether the limit of continuous functions is continuous, and it's not unless they're uniformly continuous. So Dirichlet proves, so this is Dirichlet proves in 1852 that any continuous function, and we will prove this later, on a compact interval is actually not only continuous, but uniformly continuous. It's uniformly continuous. Uniformly continuous. Implicitly assuming the Heine-Borel theorem. Okay? So this, yes?
This seems like it was before all the problems with proving a limit of continuous functions is.
Those problems are 1820s.
Oh,
So Fourier series is 1820s, Cauchy's course d'analyse is 1820s.
Okay, I got the dates.
Yeah. And in fact, this doesn't appear until I didn't write it down. But a lot of these things are sort of proved in lecture notes to students and then published 15 years later, possibly after the guys died. So implicitly assuming, so we'll go over the correct proof, but he's implicitly assuming that an interval, a closed interval, is compact.
Yeah.
Not realizing that this requires proof.
And Nardi used the product of finitely many compacts as compact.
Yes.
So,
Yeah. So this is again some more reasons that we have to develop this stuff.
it's
Really?
running off the side, but
Thank you. Good. Question. Here and then one more time your name.
Ishan.
Ishan.
Is it not true if AB is intersected with the rationals?
AB intersect the rationals is not compact because it's not closed.
But would any continuous function on AB intersect the rationals if A and B were both rational? So
How do you define continuity on a discrete? So you
it's not
could.
discrete.
Sorry.
The rationals aren't discrete.
The rationals?
Well, if A and B are irrational, then
No,
it's
no. If A and B are rational.
Oh, if just A and B. You're not saying the subset of rationals of an interval.
No.
You're saying if A and B are themselves rational.
No, you are
I was
saying
saying.
Oh, you are saying that.
I'm saying both.
What's wrong with this?
Well,
No,
how do you
very
define
confused.
continuity? Because I want to define continuity by moving continuously through something, but I can't move continuously through the rationals.
Just the epsilon delta definition seems to work. I mean, it's a
Um,
metric space.
That is true. That is true. Absolutely. With the discrete topology. So
With the standard.
with the standard topology, yeah.
Okay.
I'm not following your question.
It's not compact, so it seems as if compactness wasn't necessary for this proof. That's what I'm curious about.
No, but he wants it in the reals.
Okay, I'll just ask.
Okay,
after.
I'm not following your question.
Yeah.
Ask me again, please.
I was just wondering if the statement of Dirichlet's result should be closed interval or in compact interval.
Any continuous function, I guess I mean, yeah, he didn't have, I mean, I'm defining the modern version of what compactness means. Yes, on a closed, let's do it like that. On a closed interval, closed and bounded interval, I'm giving it away. I mean, I guess the word interval is bounded. No, interval can be unbounded. I don't know. Closed and bounded. Any continuous function on a closed and bounded interval is uniformly continuous. That is what he proved. And what he used in the proof is that, well, take an arbitrary cover of this closed and bounded interval. Of course, there must exist a finite subcover, which, of course, is what needs proving. Okay, so that's the Heine-Borel theorem. Good? So far, so good? We're all on the same page? Okay, you're going to ask me your question afterwards. You can do, I mean, yeah, as you said, it's a metric space, so you can do everything on it. Okay, so the Heine-Borel theorem. How many people know the proof of this? Okay, so I'm wasting fewer of your time. This is 1895. Well, Borel wrote it up in 1895. I guess there were some precursor ideas. Maybe Heine's the one that defined, I forget what Heine's role was. He defined compactness in our modern understanding. Okay, so what's the statement? If you have a subset of a metric space, which is it's compact, if and only if it's closed and bounded. Good. So the people that raise their hand that they know the proof, help me out. Which way do you want to go first?
Assume it's compact.
Okay. So we'll go this way. So let's say that E is compact. We claim that it's, what do you want to do first? Bounded.
Bound.
Claim that it's bounded. Bounded is easier.
yeah, so you can take
Okay. Yep. So let's take an open cover.
Take all the points.
Take all the points. How about the balls of radius r around the origin?
Yeah.
Union over all r in the reals, in the positive reals. That covers the entire space. So it contains E. And there exists a finite subcover, right? You see what I'm doing. I don't know what E is. Here's the origin. I start taking big enough balls. All the balls cover all of R, and hence they cover all of RD, and hence they cover E, and there exists a finite subcover.
It's diameter 2R.
Yeah, I'll just say there exists our finite subcover. So the union of a finite number of R, union over R1 to Rn, which of course is just the largest one of the ball of the radius of Ri of the origin, contains E. Everybody's happy. Good. That is closure. That is boundedness. Now say E is compact. Claim E is closed. By our previous theorem, it's enough to show that all limit points of E are there.
So assume a limit point.
Assume you have a limit point. We'll do a proof by contradiction, and then at the end we'll erase the contradiction. Yeah, it's easier to think when you think about contradictions. So again, I said all of my pictures are going to look like this. Here's my blob E. Here's a limit point X. Let X be a limit point of E. Okay? Assume that X is not in E. Assume that X is not in E. Now what?
Then there will be a small ball that it will be a small ball that's some point in this ball that belongs to E.
Yes. How do we make that? We want to use compactness. So we want to create an open cover. Yes?
Take open balls of around X.
Yes.
Make them arbitrarily small.
Yes, take smaller and smaller balls around X.
Now, since each one intersects E,
Okay.
I think we can take closed balls and take the complement.
Beautiful. Beautiful. So, since X is not in E, the union of closed balls of radius epsilon about X complement over all, let me not call it epsilon, let me call it R, over all real numbers. What is that? I take any ball and I take the exterior of that ball. That's open. And then I take a smaller ball and I take the exterior of that. And I take a smaller ball and I take the exterior of that. I take a smaller ball and I take the exterior of that. That's going to fill out everything except X. But X isn't in E. So it contains E. So it covers E. Since X isn't in E. E is compact. That implies there exists a finite cover. So there exists balls of radius R1 around X, closure complement, union ball of radius Rn around X, closure complement, that also contain E. And of course, these ball complements are just the whatever the smallest one. The union is whatever the largest one is, which is just a ball of radius R max around X, closure complement, contains E.
So the ball itself doesn't contain.
So the ball itself doesn't intersect E, which means there exists a ball of radius R about X whose intersection with E is the empty set, which means X is not a limit point. Contradiction, or cross out the initial assumption. If X is not a limit point, if X is not in E, then X can't be a limit point because there's a ball around X which is not in E, which intersects E, which doesn't intersect E. Does everybody see that?
Actually, we can see these two proof is as the same one because
R union the infinity point is topology equal to a sphere in R3. So in the proof of E is closed,
Yes.
so we just choose the neighborhood of infinity point, and in the proof of E is compact, we just choose the. It's like
It's that we're taking the same kind of.
yeah.
We're taking the
Just-
same
just
kind of
like,
cover, just
a sphere in R3.
just like a sphere in R3.
Yeah.
Yes.
Because R union infinity point is equal to sphere in R3, so we can treat these two proofs as a one proof.
If you like. If you like, Justin.
Are you using you're using the compactness of the sphere to prove the other end, or?
You mean how are we going to prove the other direction?
Oh no, sorry.
Is everybody happy with we've proved two things? Ask me because
the minimum is not the max.
Yeah, it should
the union of all of these balls, we have a bunch of balls that are all nested around the same center.
That's the union of
So the union of them is just the ball with the largest radius.
But it's
We're looking at the
complement.
but it's a complement.
So the smaller ball.
I'm sorry.
Yes,
You're
yes,
absolutely
yes.
right. Thank you very
Yes,
much.
I think if the
Thank you very much.
max
It's the
is,
complements I want the
doesn't
minimum.
include the E.
Was that that was your question as well? Great. Good. Okay, we proved those two directions. Let's prove the other direction. So, if we have closed, can you still see the statement? Well, maybe you don't need to see the statement. Let me leave it here in case you're still taking notes. So let's prove it the other way. So assume E is closed and bounded. We claim is that E is compact. I have a way that I like to do it, but maybe you guys have a better way, or another way. I like to do it in two steps. Step one, this is kind of an easy approach to it. Step one is that if you have a, let's say negative a to the d, so this is just a cube about the origin, this is compact.
Now we're doing.
Yeah, now we're doing RD, but there's a way of pulling this proof out and turning it into non-RD proof. And
I don't think it's valid in every metric space.
well, it's not. This isn't valid in every metric space.
The whole thing isn't, right? Like R infinity has.
Well, yes. It depends on if your metric space is assumed to satisfy the. Some people add, I want a metric space which satisfies Heine-Borel or something, which then is vacuously right. Usually, you specify whether you want this thing to be true or not. If you're doing this abstractly. Step two. So if we know that this cube is compact, then it will be enough to know that a closed subset of a compact set is compact. So if you're closed and bounded, well, then for some A you're contained in this cube, and the cube is compact, and you're a closed subset of a compact set. Therefore, you are compact. Okay? I don't know if that's the people that raised their hands and said they knew the proof. There are a variety of proofs. I find this one to be the fastest.
I like to go through sequential compactness.
You could do sequential compactness.
Two steps.
Yes. Yes. Maybe this is faster. I don't know.
Probably, yeah.
Maybe we could do both. Maybe in the interest of time. I don't know. Let's see how this goes.
But we haven't shown that sequential compactness is equivalent to compactness.
Yeah.
That's
Well,
one
that
of
would
the
be in
steps.
that would be one of the steps exactly. Right. Let me bring this down and bring this up. So I think the easier one of these is step two. Well, they're kind of both not that hard. So step two. We have a closed subset. So let's say K is a subset of E. K is closed, and E is compact. You want to prove, our claim is that K is compact. Okay, this is easy. So the claim is that K is compact. So what should we do if we want to prove something's compact? Take an open cover. Yeah. Let OI union over some arbitrary set cover K.
Can you include the complement of K to cover E as well?
Beautiful. Then the union of OI in I union the complement of K, which is an open set, contains everything. And so it contains E. But E is compact. E is compact. That implies there exists some finite subcover. So that if you take, and we may as well throw in, adding one more element doesn't change that. So finite subcover covers E. And of course everything in K complement is not needed to cover K. So that implies this finite subcover covers K. And K is compact. So far so good. All right. The last step is the proof of step 1. Proof of 1. This was proof of 2. So proof of 1. So again, let's at least to start, let's write it as proof by contradiction. So assume this is not compact. So there exists an open cover having no finite subcover. Having no finite subcover. Okay? We need to get to a contradiction. Any ideas? Tell me your name again.
Colin,
Colin.
can you just like divide the box?
Yeah, exactly.
I think 2 to the D one.
So we have this cube in RD, minus A to A, right? Minus A to A in every direction, minus A to A,
Could you raise it?
minus A to A. So that cube, let's just cut it into a finite number, in fact 2 to the D, subdivisions of half the width, half the side length. Okay? So assume this is not compact. Let's call this the rectangle R0. Then cut R0, or cover R0, cut R0 into the union of R1 L's, and the L's go from 1 to 2 to the D, although I won't worry about which one's which. Right? So each one of these little sub-regions is an R1 for some L, is a finite number. So far so good. These are closed rectangles. And of course, this is still covered by this infinite cover. If each one of those rectangles has a finite subcover, then the whole thing has a finite subcover. We assumed it doesn't have a finite subcover, so there is some rectangle, there exists some L1 such that R1 of L1 has no finite subcover by this open set. Has no finite subcover. Repeat. Everybody see that? So this guy doesn't have a finite subcover, so I keep subdividing him, and I get this guy. And he has no finite subcover, so I keep subdividing him. So we get this sequence. So continue getting a sequence, Ri, Li. There's some choice of smaller and smaller rectangles, each having no finite subcover. Now each of those is a rectangle. So there exists some point xi in each of these. In each of these rectangles, there's a point. And the diameters, there's a nested set of rectangles, and the diameters of the rectangles are shrinking. So I mean, it's kind of obvious, but I'll let you argue on your own. The set of the xi is Cauchy sequence, which implies it has a limit point. Oh, I have to say that this box is closed. Its complement is obviously open because it's the union of these half planes, right? There's a half plane there, there's a half plane there, half plane here, there, and so on. So each of these closed rectangles is obviously open. The union of open half planes, right? So it has a limit point. That means that. So what does that mean?
It's gonna be unique.
Sorry.
It's gonna be unique
So very unique as they will be
because
there are limited points. They should limit to 1 for x.
because the space is Hausdorff,
Yes.
right? So
As it
limits
should,
are
yes.
unique.
Yes. So there is a unique limit. Well, once you've made this choice, but there might be lots of Ri's that are also not covered finitely. I'm not worried about the uniqueness. I'm worried about the fact that this sequence has a limit point, and they're all limit points of R0, and R0 is closed. So R0, X is in R0. But we have this open cover,
There is an outlier.
right? So X is in one of the covers.
Yes.
This limit point X is in some OI, and all the OIs are open.
So eventually one of the cubes
So there
is
exists a
not
ball, perfect. There exists a ball that's contained in one of them, but that ball, since the diameters of these rectangles are getting smaller and smaller, that ball eventually contains some rectangle.
Do you have to say something geometric about comparing balls to rectangles?
Something rather trivial geometric, just that balls and rectangles eventually overtake one another.
Yeah.
But this is a fixed, there exists some fixed epsilon. That epsilon is fixed. So if the thing that you have to say is that for any epsilon there exists a rectangle that sits inside of it. Yes?
They generate the same topology.
Yeah, you can change.
They generate the same topology.
Yeah, you could
if
change
like.
the metric.
But this is, you don't have to say this, do you? I don't know.
Well, for the rectangles to eventually lie inside the ball, you want some statement like this. Right? I don't know.
Yes,
I don't
but
know.
okay.
Maybe
I'm
you
arguing
just
that
need
that
to
statement is
put
obvious, but
is there-
sorry.
You
Does it
prove
two
the
to-
max metric.
That's just 2 to the minus n that's really small, smaller than any epsilon.
That's 2 to the minus n. So if there's an n such that 2 to the since we're arguing about it, let's really argue about it. So there exists some n sufficiently large such that 1 over 2 to the n is smaller than, I don't know what I need, 1 over 100 times epsilon, just to be safe. It does, well, I have a ball of radius epsilon, but I'm still measuring, so by this I mean what's the side length. It all becomes a one-dimensional thing. It's a side length argument, but the ball will be times root d
Yeah, there's
to
a
the, yeah,
2 root d.
to 100 root d, let's be safe.
Okay.
Okay. This is the thing that I'm saying is trivial, but okay, let's argue about it. I'm happy to argue about it. So yes, even in d-dimensional space where you have to, balls in d-dimensional space, by the way, no, I like your question. I initially didn't like it because it's kind of like, I'm like, yeah, all right, this is a triviality. It's obvious that you take it. No, this is a deep question, actually. Because if you've ever thought about 100-dimensional sphere packings, you will realize how incredibly weird spheres are in 100-dimensional space. And if you've never thought about this, take the unit, all zeros and then a 1 in all zeros, you know what I mean, the unit cube, all ones and so on, in d-dimensional space, and put a ball of radius 1/2 around each. And compute, so there's some ball that exactly sits in here. So I've drawn a 2-dimensional, so it's extremely deceiving. Our experience is not at all what actually is going on. Compute the volume of the radius of the largest ball you can fit in here. And you will be shocked. I'm not going to give it away to you. Okay? So that's an excellent point. I changed my mind about your point. I like your point. Yes.
This may be a slight non sequitur, but do you have any intuition for why that issue occurs? I know what
This issue?
Yes.
Because we have no, well, why it occurs is a simple calculation, but why it's such a shock is because we live in R3.
More than, was there some intuition for why one would, if we can change our intuition, right, could we have expected this?
Yes, you do the calculation and then you say, now I get it, that's not what happened. What I think happens is not what happens. And
Right.
yeah. I don't know if I answered your question. I owe you two things now at the end of class.
Yeah.
Okay, so one more comment, question?
I heard of it. That's the radius of the small ball converging to 0.
I don't want to give it away. Play with it. It's a very easy computation. Play with it. It's very fun. Okay, so if you believe me, and we've had this discussion now, that there is some small enough rectangle that will completely sit inside this ball, that means you've covered that rectangle. But that's a contradiction because we assumed none of these rectangles had finite subcovers. Alternatively, we've constructed a finite subcover given a cover. Either way, this proves the compactness. Implies, where are we? R0 is compact. Is everyone happy with that? Is anyone unhappy with that?
So yeah, I guess I have a question.
Charlie.
So, Andre.
Andre.
Charlie.
Charlie. Okay, I'm getting my geography off. Andre.
Yeah. So what happens if many of the, when you subdivide into cubes, what happens if many of them end up having infinitely many open sets?
Okay, so this is the, do we really not want to do this by contradiction? So by contradiction, this is the proof. If you want to then go back and undo the contradiction, then you're dealing with what you just said.
Yeah.
Because then you want to cover all of them, every conceivable time that this happens.
Yeah, because here we just got to the contradiction.
Yes.
And that's it.
And that's it.
You can't have one that does it.
That's
Yeah,
right.
That's what we proved.
That's it. Okay? All right. Heine-Borel. What else can I do in 5 minutes? All right, let's throw a few definitions up and then we will. All right, any questions on Heine-Borel? Compact is equivalent to close and bound. Let's do a few more little computations. I know what I can do in 5 minutes. I can construct a Cantor set. That takes 5 minutes. What page is this? 6. All right. A few more definitions. What does it mean for a point to be isolated?
What exists in the ball radius epsilon
Yep.
that only contains x?
Perfect. Can you see that? If there exists some r so that the ball of radius r about x intersect with E is just a singleton x. Okay, so here's E, here's x. X is isolated. There's some ball whose intersection with E is only x. Okay. What's it mean to be an interior point? Is an interior point if
Exists some open boson that won't contain this.
yes, it's the very thing that we talked about for open. Open is that every point is an interior point. If there exists some r, so that the ball of radius r is completely contained inside E. So I could have defined interior first and then said a set is open if every point is an interior point. What is the interior of a set? This is the set of interior points, the set of x in E that are interior. Do I even need a lemma that this is open, or is this completely obviously open? This is obviously open. It is. Okay, this is by definition the interior of E, and it is open, and that equal sign is a trivial argument. Less trivial argument is that the closure. So we define the limit. We define the set of limit points. So this is E union the set of limit points of E. Yes?
I'm not sure the the interior of E, or the E to the 0 thing is trivial, just because it may contain the, it may be that, that each open ball contains points which are not in the interior.
They would have to be because the ball is open though, right? Because like you could then, there's
Sure,
a point in
sure.
that ball,
Well,
you
you
could
have to
throw a
do
ball.
That's what
around
this little argument is. Yeah.
Okay.
It's that balls are open or something.
Okay, I just wanted to note that it wasn't just true.
It's not trivial. Yes, it's almost not trivial. This is much less trivial, for a good reason that we'll talk about in a second. I guess I won't do the Cantor set today. E union its limit points is called the closure of E, and now there is something to prove, which is
It's closed.
It's
You don't-
closed.
You don't add any new limit points.
you don't add new limit points. There are no limit points of the limit points that weren't already limit points of E.
Some kind of diagonal.
It's easier than that. Let's call this a lemma. E bar is closed. Any ideas?
The limit point of E bar.
Yeah, take a limit point of E bar. I just want to see. All right, fine. Let's prove this. Proof. Let x be a limit point of E bar, and of course, what I want to claim is it's also a limit point of E. In which case, it's in E bar. So what does it mean to be a limit point? Again, here's my E. I don't know why it's the same picture every time. So there's some. So for all epsilon, there's the ball of radius epsilon about x intersect E bar is non-trivial.
Yeah. Could we start off by saying, like, say if X were a limit point of E itself, then we're already done because it has to be in the closure? And then say, like, if it's not
Sure.
a limit point of E?
Okay.
I don't know, maybe you have a different idea.
Well, I was about to prove that it is a limit point of
Well,
E.
let's do that then.
Yeah. It's the same thing you told me to do the other
Yeah.
time. Take out the contradiction at the end. Contradictions are very useful for finding arguments, and then you just remove it from the top and the bottom, and then there's the argument. So there's a bunch of points, right? So what is it? So let for each epsilon, I don't know if you want to do this with 1 over n's or something. Now I'm trying to rush. Whenever I rush, because I'm watching the clock, it ends up taking longer than if I would just slow down and go at a leisurely pace, and everyone will understand everything. So let's do it like this. For all 1 over n, the ball of radius 1 over n of x intersect E bar is not the empty set. I.e., this ball, this intersection contains a point. There's a point xn, which is in E bar, which is in E bar. Okay? Now, each of the xn's, if they are limit points, if they're not in E, so my claim is that if it's not in E, then I can switch to somebody else who is in E.
Mhm.
If xn is not in E itself, there exists, my claim is that there exists a yn, which is also in this ball, intersect E now, and not E bar. Okay? Why is that? If not, if there is no E in this range,
Is it that ball? I mean, that ball is an open set containing yn.
yes.
So, by definition of limit point, it has
The fact
to
that, yes,
intersect.
that this thing, if it's not an E,
Has to be a limit point.
has to be a limit point, and so there's a yn. So it's either in E already, or so yn could be xn itself, or not. Okay, once you switch to this, that means that x is a limit point of E itself, and that means that it's already, which implies that x is in E bar. So every limit point of E bar is in E bar, so E bar is closed. All right, we'll do the Cantor set next time, and I will push the homework, which has the Cantor set in it, to Friday so that we at least have a chance to talk about it on Tuesday, and I will email you about an office hour on Tuesday so that we can talk about this more. Any questions? Very good.
So when?